Okay, let's full screen this guy. Okay, sorry about being late once again, but this shouldn't take me very long to finish everything up. So what I'll cover today, it's a final exam review, so I'm gonna again remind you about the final exam, where it's gonna be, what time you're supposed to write it, and so on, just to be sure that you don't go to the wrong room. It has happened before. And I'll give you what the layout of the final exam should be, what is expected, so what topics you're supposed to cover, how many questions, and so on. So I'll give you that today. And then we'll cover some review questions. So I'll only be covering the computational questions for the problem sets. The theoretical ones you can pretty much read on your own. There's no point in rehashing those, but I want to show you exactly how to get the actual answers for the computational problems in the problem set. So we're going to split this up into 2, maybe 3 parts, depending on how we go, but I should be able to finish in about an hour and a half. First part is just talking about neural network training, so doing forward and backward propagation, stochastic gradient descent on training a neural network, and then we'll get on to calculating k-means, skew data evaluation, just a very simple example, and then we'll get on to self-organizing maps for the last part of the review. Okay, so final exam, date and location, time. Just want to make sure everyone's on the same track. I will post this again on the course website just to be sure that you know exactly where to go. I put this information up about a month ago, but it got lost in the news feed, so I'll make sure to refresh that just to remind you where you're supposed to write. So again, it's on Tuesday, April 26th, this year, from 3 to 6 p.m. And then depending on which section you're in and depending what course you're in, you're split up into 3 different rooms. So we're pretty much going to occupy the entire 5th floor and some of the 6th. So if you're in section 1 and 2, you're right in the SHE building, 554. If you're in section 3.1 and 4.1, you're in 652. This is for ELE today, the undergraduate stream. If you're in the graduate stream, you get a room all to yourself, which is the SHE building 540. Okay, SHE building is 87 Gerard Street West, Easter Church and Gerard. If you don't know where it is, you can either look it up on Google Maps or take a look at the official campus map for more details. All right, so final exam information. So some profs like to ask you material before the midterm. I don't like to do that because I've already tested you on that stuff, so you don't have to study anything before the midterm. Do not study anything before the midterm. You're wasting your time, okay? Only study stuff after the midterm. So from neural networks onwards to the end is what you're responsible for. Obviously, any topics that you have to know that carry on to the second half of the course, like training parameters and training model, that kind of vocabulary you're supposed to know, it's just assumed. Okay, so just study neural networks and onwards to the end. So you're not responsible for the first half of the course. I don't like asking questions before the midterm because I've already tested you on it, there's no point. Okay, so the topics covered, so general concepts before the midterm that carry over, yes, you're responsible. The topics covered for the final exam officially are as follows. So first you start off with neural networks, so general concepts, what a weight is, what a neuron is, just stuff that you're supposed to know. And then how to calculate forward and backward propagation, obviously, and then stochastic gradient descent for training. So you need to know the process of training a neural network with stochastic gradient descent. Okay, and then support vector machines, general concepts. I won't ask you to do anything computational in nature, just understand what the purpose of SVMs are, what they do, know what the kernel trick is, and different kinds of kernels, and the way it's supposed to work, support vectors and all that. And then no concepts of machine learning system design, so no bias and variance, know what cross-validation is, learning curves, precision recall, F1 score, know those concepts, just the concepts, there's not any computational in nature other than calculating precision recall, which is pretty simple. And then we'll get on to k-means, so make sure you know exactly how k-means works, especially the clustering algorithm, how to calculate centroids, how to calculate memberships and all that. We'll do an example in class, of course. And then know about dimensionality reduction. So obviously there's no computation in nature. That's all done in MATLAB for you, but know exactly what the process is. You take the SVD, you take the first few columns of the V matrix, multiply it with your mean centralized data matrix and so on. So know the process behind how to go from reduction back to reconstruction. And then self-organizing maps, just the general concepts, and also how to train a self-organizing map, which I'll cover in class today. Just one example. And then just general concepts on genetic algorithms, particle swarm optimization, ant colony. So we've only covered stuff in a theoretical nature. I just know exactly how the algorithms work. I'm not asking you to compute anything, so know the theory only. There's no explicit calculations, just know in a general sense how the algorithms work. That's what you're expected to know. Okay? So with the final exam, I've learned my lesson, so there's only going to be 4 questions. All right, that should take you about 3 hours to do. So again, 1 theory-based, so no general concepts as we stated above, no pretty much anything in terms of the general concepts, and then there will be 3 calculation-based questions. So if you can see here, there's only 3 topics that we've covered that are calculation-based. So you can kind of infer what's going to kind of be asked in terms of the calculation-based questions. Okay? So what you are allowed is just the same as before. You're allowed a non-programmable scientific calculator, so no TI-83s or any of that thing with a graphic nature, just scientific calculator that is non-programmable and doesn't have a substantial amount of memory. And in this case, with the final exam, because there are more topics to cover, you are allowed a double-sided handwritten formula sheet this time. You can put whatever you want on it, I don't care, as long as it's handwritten by you. No photocopies. You can print it out if you write it out on a Surface or a tablet or something and print that out, that's fine, but no computer-typed formula sheets, all right? So any handwritten, no photocopies and so on. Okay, so that is what is expected to be covered. Okay, so without further ado, let's get on to the review. We're going to cover the first question, which I believe is from week 6. So this is week 6. This is just the last question. This was just prepping you on how to calculate forward and back propagation, just practice. So this is the neural network that we had. Okay. So we see here that this is a 2 hidden layer, 1 input, 1 output layer neural network. So we see here that these are the bias units. All right. So these are the bias units. This stuff here. All right. And then we see here that there's only 1 input neuron, which is nice. It makes things less complicated. Okay, and then we have 2 hidden layers. So we have 1 and 2. So we have 2 neurons for, hidden layer 1. We have 1 neuron. This is not including the bias. Okay, and then finally 1 neuron for the output. Okay. So this is the structure that we have. We also have the following information. We see that the activation function is the hyperbolic tan, or it's simply e to the z minus e to the minus z over the same stuff as above, but you're adding a plus. If you don't want to bother calculating this, there's a button on your calculator that says tan h. Just simply use that. All right. And also the derivative of this is equal to 1 minus the activation itself all squared. I'm not going to derive this for you. You can verify that yourself, but that is certainly, you can express the derivative of the hyperbolic time with respect to itself squared. So, yeah. Okay, forgot about that. Okay, great. Okay, so we initialize the neural network weights to be the following. All right, so the weights between the the input layer and the first hidden layer are as follows. So you got 0.1, 0.2. Okay. So just as a reminder, when you traverse down this way, these are the nodes for previous layer. In this case, this is 0, and these are the nodes for current layer. In this case, 1. All right. So what the 0.3 means is that it is a connection from the second node of the previous layer to the first node of the. Let me see here. Sorry, no, this way. So it's the connection between. Let me see, 1, 2. Sorry, this is the first nodes from the previous layer. That's fine. So it's a connection. Yes, sorry, it's a connection between the first. Let's see here, what's going on? Wow, that's a little messed up. Let's see. Okay, so sorry, this is the first layer into. Oh, my bad. Yeah, sorry, bias unit. Oh, sorry, my bad. Okay. So this is including. So this here is the bias unit. Sorry, I misread that. And this is the input layer. So remember the first row counts as the bias, and the second row and onwards are the neurons that are not for the bias. So for example, if you take a look at this one here, 0.3, it's the connection between the input neuron and the second node of the hidden layer. Okay, so you go down vertically to figure out which neuron you want to select in the input layer, the previous layer, and you go horizontally to figure out which node you want to select in the previous layer. So 0.3 means choose the second neuron here, and that connects to sorry. The first one here connects to the second one there. Second to first. So second here and to the first one here. This is not including so there's no connections to the bias. Okay, so that's how you do it. So second node, which is this guy here, you connect to the first node without the bias to the next layer. So that's how you calculate it. Okay, so that's the first matrix. The second matrix is, let's see, it's 0.2, 1 minus 3, okay? And finally, the last one is just 1 and 2. Okay, so remember the notation is you go down vertically is selecting which node you want in the input layer or the previous layer, and horizontally is selecting which node you want to connect to in the next layer. Okay, so, all right. So let's see here. I've got all that down. All right, so the question asks you, so if you're given x equals 2 and y equals 1, we want you to practice calculating the forward and back prop. Okay, so you have to calculate forward and backward propagation. That's the question that we ask you. Okay, so if you remember what the algorithm was, you initialize the input layer to be the actual input itself. Right, so this is the input into the first layer. What you do is you append a bias, right? And then you add in the actual input itself. So this is your bias, which is always 1. Okay, and then these are the inputs. In that case, it's 2, so there's just 1 for now. Okay, so now what you want to do is you want to calculate all the inputs that are coming into the first hidden layer. So if you remember what that was, you just did a lab recently, it's equal to, you take the matrix that goes from the previous to the current layer, you take the transpose, then you multiply by the inputs that are coming in. Okay, so you just have to transpose W1. In this case, you have 0.1, 0.2. Okay, so you just flip the rows and the columns, and then you have 1 and 2. Okay, so when you actually calculate this, it's quite simple. You have 0.1 times 1 and 0.3 times 2 is 0.7. Okay, and 0.2, and then 0.4 times 2 is 8, so that's 1. Okay, fantastic. So for forward propagation, you have to calculate x. You have to calculate x and then s, and then you keep going till the very end. So when you want to calculate the outputs from the first hidden layer, what you do is you append a bias again, and then what's going to happen is that you take each of these inputs, and you have to apply the sigmoidal function, not sigmoidal, the activation function to each of those inputs. So you have g of 0.7, g of 1. Okay, so when you calculate this, and we'll bore you with the details, this actually is equal to 1, 0.6044, and 0.7066. Okay, so those are the outputs from the first hidden layer, and these are going to go serve as inputs into the neurons for the second hidden layer. So you just repeat the process. So in this case, you take the second weight matrix, transpose that, multiply by first one. Okay, so the second weight matrix was just 1 column. When you transpose that, it becomes 1 row. So you get 0.2, 1 minus 3, and then take this and you go 1, 0.6044, 0.7066. So this is just a dot product of 2 vectors. So when you calculate this, you get minus 1.4804. Okay, that's fantastic. So we've got that. So this is the inputs into the second hidden layer. So now you have to calculate what the outputs are from the second hidden layer. So you just create a vector, so you have 1, and then you take any inputs that are coming in from the second hidden layer, you apply the activation function to each of those elements. In this case, we just have 1 here. Okay, so when you calculate this, we get 1 and then minus 0.9015. Okay, so remember this is the output of the second hidden layer, right? So we still have 1 more. We still have the output of this layer over here. So in this case, we have to calculate the inputs that are coming in. So we have W3 transpose times x of 2. Okay, so what was it? It was 1 and 2. So we transpose that, we got 1 and 2. Okay, and then 1 and minus 0.9015, right, from the previous part. And then when we calculate this, we get minus 0.8031. Okay, last but not least, you calculate the final output in this case, you don't have to append a bias, it's up to you, but we remove the bias in the end, right? So you just calculate what the activation is for the input that's coming in. And okay, in that case, you get minus 0.6658. Okay, so this process that we did was forward propagation. So let me just write this down. So this here is forward prop. Okay, so the goal of forward propagation is to remember all these inputs, so X and S. So you have to remember all the X and S's until you get to the very end. Okay, so that's forward prop. Now what you have to do is you have to calculate the sensitivities and the error gradients for each of the weights. So you have to do backpropagation now. Okay, so remember what you have to do is you have to calculate all the delta terms first. So if you want to calculate the last one, all you have to do is take the output from the, this is the predicted output from the output layer. You subtract this with the expected output, and then you do an element-wise product with the signal S of 3 with the derivative of the signal 1. So you're doing this element-wise. Okay? So X of 3 was equal to what? Minus 0.6658. Okay? And then Y was equal to 1, I believe, yes, so 1. Okay? And now you have to do G. So we are going to do 1 minus, because remember G prime of Z is equal to 1 minus Z by itself. Okay? Now, when you do this, G of S of 3, okay, all squared. If you take a look at what we calculated before, G of S of 3 is actually this guy right over here. Right? So there's no point, so all you have to do is just take this output here and substitute that for this term inside here. Because we've already calculated G of S of 3, so you just plug that into here instead. Okay, so you have minus 0.6658. So, element-wise, it's just one, scalar is pretty, it's unambiguous. You're just doing a multiplication, so you have 1 minus 0.6658 squared. Okay? Because G of S of 3 is defined as what X of 3 is. That's what we have here, so that's why you're just substituting that in there. Okay? So when you calculate this, you get minus 0.9274. Okay. So that's the sensitivity for the output layer. So now what you have to do now is you have to calculate all the sensitivities backwards. So you're starting from the output layer and then you're going all the way backwards, back to the hidden, through the hidden layers and finally back to the input layer. So the equation for this, all right, take the derivative of the sigmoid with the corresponding inputs that are coming into the second hidden layer, and then you multiply this by, take the weight matrix, right, 3 and then delta 3. Okay, so what this is that you take the weight matrix from the third, connecting from the second hidden layer to the output layer, and you remove the first row. So if you remember what the weight matrix was for the third one, from the hidden to the output, it was equal to 1 and 2, right? So this tilde means that you get rid of the first row. So in this case, we don't need the bias unit there, or the weight to the bias. Okay, so in this case, we have 1, so S2 was equal to what? It was, here we go, so it's just this guy here. Okay, so there's only one single output. Okay, so we have S2. Now, to save time, all right, here, this essentially is equal to G of S2 here, okay, and which is equal to minus 0.0915. So I'm just going to take this and substitute it below. So in this case, you have 1 minus, well, I'll just write this in just to, just for the sake of completeness. Okay, in this case we have 2, and then multiplied by the sensitivity from the previous layer, which is minus 0.9274. Okay, so in this case we have 1 minus, and then this was, what is it? Minus 0.9055. Okay, and then 2. Okay, remember this guy here is just equal to the output from the, it's equal to the, it's the output from the, from the hidden layer to the output. Okay, so when you multiply all this out, we get minus 0.3475. Okay, so that's the sensitivity for the, between the, first and second. And finally, we gotta get the sensitivity between the input and the first. So just repeat the process. Okay, so the standard formula is when you want to calculate the sensitivities for the, first, for the layer L or layer, small l, you take the inputs that are going into the neuron for that particular layer, you apply the derivative of the sigmoid to it, and then you take the weight matrix from the next layer, remove the first row, and then just multiply by the sensitivity from the next layer. Okay. All right. So let's see here. So W2 is equal to what? This is equal to, what did I have here? It was 0.2, 1, and 3. So if you want to remove the first row, you just get rid of that. So in this case, I'll fill the left side out in a minute. This is element-wise, okay? My bad, I make sure you put element-wise in there. So you have 1, 3, okay? And delta 2 is equal to minus 0.3475, okay? So if you want to calculate this, all you do is you find the derivative of the sigmoid for each of the terms for S of 1. So S1, let me see here, it was 0.7 and 1. So what you're doing here is you're doing 1 minus G 0.7 all squared, 1 minus G of 1 all squared. Okay, so instead of you recomputing this again, if you just take a look, so we used S1, and then what you do, all you have to do is just take a look at S1. So if you take a look, these are already computed for you. So you can see that this is saving time. So every time you want to compute the derivative of the term, just take a look at the corresponding x values for each of them. So in this case, we just have these values. You're going to take those values and substitute them below. So in this case, you have 1 minus and then 0.6044 squared. Sorry, that's a little bad. And then you have 1 minus, what was it, 0.60 and 0.766. 0.766 squared, multiplied like this. Okay, then you have the 1 over 3. We just put that in bracket. Sorry? Yes. Just making sure you're paying attention. Okay? Yes, minus 3, thank you. So when you do this, so minus 3 again, so when you calculate this, the output finally is equal to, what do I have here? I did all the calculations beforehand, so I don't have to bore with all the details. But finally, we get minus 0.2204 and 0.4375. Pretty sure if I can, okay, that's good. So now that you have this, so you have your sensitivities, now what you want to do is you want to calculate the updates. So these are the updates you'd apply to each of the weights when you want to go, before you go to the next step. So you take the outputs from the hidden layer, multiply by the sensitivities between the input and the hidden. You take the transpose of that. So in this case, x of 0 was 1 and 2, and delta 1 is equal to minus 204. Remember, this is the transpose, so each of the rows become the columns and vice versa. So this is what's known as the outer product. So how you actually calculate this is that you simply take each of these numbers and scale each row by that number. So what's going to happen is that you're going to produce a matrix where the first row is just take this row and scale by 1. Okay? And then this row will just be the top just multiplied by 2. In this case, it's minus 0.4408 and 0.875. All right, so that's the those are the updates you'd apply between the first and second. Sorry, the first, no, the input, the input in first. Then you calculate this again for second one. Okay, in this case, x of 1 was equal to, what did I have before? Okay, so it was 1, 0.644, 7066. Okay, and then delta 2 is equal to just the constant minus 0.3745. Okay, this is just a scalar multiplication, so when you multiply this out, you get minus 0.3475. Okay, you get minus 0.2099 and minus 0.2645. Okay, so those are the weights between the first and second hidden layer. And finally, you have the weights between the second hidden layer and the output. So it's just the outputs from the second hidden layer with the sensitivities from the final layer. Okay, so x2, let me see here, what was that? It was, okay, so we've got 1 minus 0.9015, and then delta 3 was just minus, let's see, minus 9274. So when you multiply this out, very easy. and then multiply these two together, we get 0.8766. Okay. And that is it. Okay. And that's how you calculate. So that is the procedure you go. So calculating the forward propagation, calculating the backward propagation, and then you have these matrices, the gradients for the first, second, and third weights. You add them on top of what the current weights would be, and that would be the update that you would have to go to the next iteration. Multiplied by learning rate, of course, but we're not doing that here. Okay? It's just a little bit of a warm-up. All right? So I'll do another question, and it'll be pretty much like this again. We're going to have more practice, but in this case, we're actually going to try to train a neural network. We're going to have multiple examples. We're going to update the weights, and we're going to iterate. Okay, but any questions here so far? Okay, good. So this you pretty much should know because this was just recently in your last lab. So doing all these calculations. Okay. All right. So week number 7. Okay, so we have this question, which is this guy. It's going to be a little more complicated. Okay. So we're going to still use the same activation function again. So we're going to use the hyperbolic tan. And just to remind you that the derivative of this activation function is simply 1 minus itself squared. Okay. And we are given a learning rate of 0.75. So that's the alpha. It stays constant throughout the rest of the rest of the time here. And we also have 2 examples. Okay, we also see here that we have 2 features. So we have x1, x2, and then y. All right. So in this case, we have, let's see, we have 2, 3, and this is just coming from straight from the document. This is the week 7 problem set. Okay, so we have 2 examples learning rate. And you see it's all described here. So you have 2 neurons plus a bias for the input, 2 neurons plus a bias for the hidden, and then we have the second one, just 1 plus the bias for the next hidden, and then finally the output. And now we're given the following weight matrices. So these are the initial weights. Okay, so the first matrix, okay, is equal to minus 0.01, 0.01, 0.02, minus 0.02, and finally minus 0.01 and 0.02. So these are the initial matrices. The second one is 0.01, 0.03, 0.02. Finally, the last one is just 2 elements, which is minus 0.05 and 0.05. Okay, just as practice, right? So we see here that the weights are unlabeled. So if you want to draw the weights to each of these, remember that the horizontal here, so when you're going down this way, this indexes the row from the first layer, or the neurons from the first layer. So in this case here, if I wanted to figure out where this node is connected to, then remember this is the bias, this is the first, and this is the second here. And then we have hidden layer 1 and hidden layer 2. So in this case, this connects from the bias to the first node of the hidden layer without the biases. So this would be minus 0.01 here. Okay, so this weight here, bias to hidden layer 2, this here will be 0.01. And then just more practice, let's say I wanted to do this one here. In this case, this connects between x1 and the second node of the hidden layer, which is this guy right here. This would be minus 0.02, and so on. Okay, so if there's a question that says, here are a bunch of weight matrices, draw what the neural network would look like, that's what I would expect you to do, just hypothetically if I were to ask. Okay, just one more. Let's say I wanted to draw this guy. So this is saying here that I want to draw from x2 to the first node of the hidden layer here, and this node, this weight here, is minus 0.01, and so on and so forth. So let's say hypothetically, if I were to ask you, I don't draw this picture for you. I say here are a bunch of weight matrices. You draw the neural network yourself. Knowing this, you should be able to draw it on your own. Okay, so just hypothetically, if I were to ask you something like that. Okay, so anyway, so those are the initial weights. And then what we want to do now is they want us to compute 2 epochs of stochastic gradient descent. Okay, So what I'm going to do is I'm going to show you in full detail what the first epoch will look like, and then I'll leave the second epoch for you as an exercise. Okay, I don't want to bore you with all the detail. I just want to give you enough to get you started so you know exactly how the computations work, and then you can go ahead and do the other steps on your own. And the answers are obviously posted online, but I'll show you a detailed calculation of how one epoch works. Okay, so remember with stochastic gradient descent, what you have to do is you have to randomly shuffle your examples before you start doing this. So in the problem set, it just tells you to assume that the data set's already shuffled. So there's no need for you to do any shuffling. Okay, so this is assume shuffled examples. Okay, so that's already implied. So you just have to go in order with these. So we have two features, and this is the expected output. There's only one output layer neuron here. Okay, so we're going to do the first epoch. Okay, so what we're going to do is we're going to take a look at the first example. Okay, in this case, this is example 1. We have two features, which is 2 and 3. Okay, and the expected output is minus 0.5. So what they want us to do is they want us to compute forward and back propagation, compute the updates, and then update your weight matrices after that's done. Okay, so we're just going to repeat what we did previously, but we're going to do an extra step and actually update the actual weight matrices themselves. Okay, so let's calculate the forward propagation. Okay, so what you need to do first is you have to initialize the input layer to have a bias unit, and then you take each of the features of interest and you just put them into your column vector as so. Okay, that's fantastic. Okay, now what you need to do is you have to calculate the inputs that are coming into each of the neurons in the first hidden layer for all of them individually. So in this case, it's just taking the weight matrix that corresponds to connecting between the input and the first hidden layer, you transpose that, and then you multiply by the inputs that are outputs coming in from the hidden layer. Okay, so W1, you're going to transpose this. So just take all the rows and make them columns. So this is minus 0.01, 0.01, 0.02, minus 0.02, and minus 0.01, 0.02. You multiply this by 1, 2, and 3. Okay? So when you calculate this computation, very simple, what's going to happen is this becomes 0 and 0.03. All right? So you can verify it yourself. So you have minus 0.01 times 1, and then you have plus 0.02 times 2. So minus 0.01 plus 0.04 is 0.03. And then when you add this with 3 times minus 0.01, you have the minus 0.03s. When you add them up, they cancel out. And then you go ahead and verify that with the other one as well. So it's just simple matrix vector multiplication. So that's the inputs that are coming into the first hidden layer. Now what you have to do is you have to calculate the outputs that are coming out from the first hidden layer. So you append a bias unit, and then you apply the activation function to each of these elements individually. Okay? So in this case, what we have here, okay. So actually, I fudged the numbers actually on, I don't know why, but when you actually plug in these numbers into the activation function, you actually get something very similarly close to what's coming in as the input. So it actually tripped me out a little bit, but I fudged the numbers unfortunately. So you actually get almost the same output because they're very close to 0. So I probably should have made the weight matrices probably a little larger, but that's the way it goes. Okay, so now we gotta compute the inputs that are coming into the second hidden layer, feeding from the outputs of the first hidden layer. So what you do next is you take the weight matrix, that connects between the first and second hidden layer, take the transpose of that, and then you multiply by the outputs that are coming from the first hidden layer, which is like so. Okay, so W2 transpose is equal to, let's see here what we have. Okay, so this becomes 0.01, 0.03, 0.02. Right, so all of the columns become the rows and so on, and you get 1, 0, 0.03. All right, let's see, do I have that? Yes, I do, good. In this case, we get 0.0106, just losing track of where I am. Okay, so those are the inputs that are coming into the second hidden layer. Now we have to calculate the outputs that are coming out of the second hidden layer. So you have 1, and then G of 0.0106. Okay, So when I calculate this, it's pretty much almost the same because it's very close to 0. So obviously when I make the final exam questions and all that, you will see a difference when you plug the activation function in. I chose these numbers at random, and when I was actually working out the examples, I'm like, oh, the number's actually pretty close, so that was unintentional. Okay, so those are the outputs coming from the second hidden layer, and now we have to calculate the inputs that are coming into the output layer. So this is equal to W3, so the weight matrix, you transpose this, multiply by the outputs that are coming from the previous layer. Okay, so in this case, W3 is equal to minus 0.05, 0.05, and then 0.05, transpose this, and then we have 1, and then 0.0106. Okay, so when you calculate this, we get minus 0.0495. And then finally, when you want to calculate the output, the predicted output, we get G of, we actually get 1 decimal off. So it's actually 494 this time when I calculated it, which is okay, I suppose. All right, so this is forward and backward prop. So you're starting from the input layer, you do the calculations, figure out what the inputs are coming into each neuron, figure out what the outputs are, keep going until you get to the very end, and make sure you remember all these because now you have to use these to calculate your back prop. Okay, so that's all done. We go back propagation now. Okay, so when you do back propagation, you always start with the output layer first, and then you chain back, and then you go back to finally towards the input layer. So the last layer is equal to the expected output. Okay, subtract the training example output, the expected output, and then you multiply this element-wise by the inputs into the current output layer, the derivative of that. Okay, so in this case, we see here that this is minus 0.0494, okay? And the output, the expected output was minus 0.5, so minus 0.5, okay? Element-wise multiply this with, and you have 1 minus G of S of 3, which is minus 0.0495 squared. Now you don't have to calculate this again. Remember, you've already calculated above. You see here, G of minus 0.0495 is this guy right here. So you just plug it in right here itself. So what's nice about this is that you've already calculated a lot of these things. There's no point in you actually doing the calculation again. So just to save time, that's what you do. Okay. So plus, so we got 0.0006. Okay. And then you'll have 1 minus. I think that's what it is. Yeah, just looking. Okay. Actually, no, that's not 0.0, my bad. Whatever that is, I think it's 0.4 something. Okay, I'm going to leave that by itself because it's not a small number. So this is plus. Okay, so 0.494 squared. Okay, and this number actually outputs, what is it? It was 0.4495. So, okay, so there's a increase in magnitude by a factor of 10, which is nice. Okay, so that's the output for that's the sensitivity for the output layer. Now you have to chain back and do it for the rest of the layers. In this case, we have it's G, okay? And you multiply this by, take the weight matrix for the next layer and multiply this for the sensitivity of the next layer as well. So just a reminder, the weight matrix for the, between the, the second hidden layer and the output is equal to, minus 0.05 and 0.05, okay? So this tilde means that you're supposed to remove the first row. In this case, you just get rid of this, okay? So if you had a matrix that had more than one column, just remove the first row, okay? So we have 1 minus G of S of 2. Okay, and then we have 0.05. We remove the first row, and delta 3 was 0.4495. Okay, so we calculated this already. This is simply equal to x of 2 like we did before, without the bias, right? So we've already, let's see here, s of 2 was equal to this guy right here, this right here. This is g of s of 2. In this case, it's just 0.0106. So just calculate 1 minus 0.006, okay, and whatever this number is. Okay, so when you calculate this, finally, we get 0.0225. Okay, so that's the sensitivity for the in between the first and second hidden layer. And finally, you want to calculate it between the input and the first. So just do the same computation again, but you're just going backwards one layer. So 2 and, okay. So this white matrix here from before, it is equal to, let's see here, it was, oh, sorry. It was 0.01, 0.03, 0.02. Okay, so you want to remove the first row. So in this case, get rid of this entry, and you're left with just these two. In this case, you get 1 minus g of s of 1. This is all squared, and then you element-wise product this with, it's implied to do this as well, but there's only a scalar, so it doesn't really matter. So we have 0.03, 0.02, and then delta 2 is equal to this guy, so this is 0.0225. Okay, so g of S1 we've already calculated, so if you go back up, right here, okay, yep, so this is element-wise. So if you see here, this is now a vector, so if you take a look, so this here is what I'm looking for, so these two numbers here. So this would be g of s of 1. So this is a vector, okay? So I need to do the same thing, but I have to apply the derivative of each of those terms. So in this case, we get 1 minus, and then we have g of, 0 and 0.3, okay. Let me just write these down, and I'll square them at the end. Okay, and then you multiply this by, 0.03, 0.02, and then, okay, so each of these terms, I think was just equal by themselves. It's good. So when you plug in this here, becomes 0. This here becomes 0.03, and then when you do this calculation and all that, what we get in the end is a matrix which is actually, the updates are actually very tiny. Okay, so that's finally in the end of there. Okay, so we have those. Now what we need to do next is we have to calculate the error gradients. Okay, so when you do that, we get, let's see here, so we had the first one. Okay, so we had, I believe this was 1, is it 1, 2, 3? Yes, 1, 2, 3. And then delta 1 is equal to 0.0007, 0.0004. Okay, this is the outer product. So what you're going to do is you're going to take each of these numbers here and scale them by the rows here to produce a 3x2 matrix. So you get 0.0007, 0.0004, and then you multiply this by 2, and then you finally multiply this by 3. And we're good. We're good to go. Okay, and that's the error gradient for the first one. Then you just do the same thing for the second one. So this is x of 1 delta 2 transpose. So x of 1 was equal to what? It was, okay, 1, no, it's 1, 0, 0.3. Okay, so 1, 0, 0.03. Okay, and then delta 2 was, this guy's 0.025, 225, sorry. Okay, so when you calculate this, we get 0.0225, 0, and when you multiply these two numbers together, it's actually quite a small number. Okay, so we get that. Finally, you calculate it for the connections between the second hidden layer to the last, which is the output layer. In this case, you have x of 2, delta 3. Okay, so x of 2 was, let me just double check here, it was 1 and 0.016. 0.106, sorry. And delta 3, that sensitivity I just calculated, which was 0.4495. Okay, so when you calculate this, we get 0.0, sorry, not 0.4495, not 0. Okay, and then when you multiply these together, you get 0.0048. Okay, so these matrices are what I actually want. Now what you have to do is you have to calculate the update. So you take the matrix that is right now, what it is currently, and then you have to do gradient descent. So alpha and then times. There's only one example. So when you divide by m, technically it's equal to 1. So in this case, the first matrix was equal to minus 0.01, 0.01, 0.02, minus 0.02, and minus 0.01, 0.02, yes. And then the learning rate was 0.75, okay? And then you just simply take this white matrix that you calculated from above and just multiply that by the learning rate. So I'm just going to copy that and just avoid, unnecessarily writing things too many times. So when you do this, when you calculate this, the final update to this matrix that you have is equal to minus 0.0105, 0.0097, 0.019, minus 0.0207, and then the last rows are just minus 0.0111 and 0.0012. Okay, so that's the weight matrix. That's what the updated weight matrix would be once you calculate the gradients. And then you just repeat this for the other matrices. So it's quite simple. So you just take the current matrix that it is right now, apply your learning rate, and then just apply the gradient for that particular matrix. So the second one was equal to 0.01, 0.03, 0.02, minus 0.75, and then I'll just take the weight matrix from before, like up here. No, I don't want to, it's faster if I just copy. Okay, so when you do this, when I compute this, this update here is equal to minus 0.0069 and 0.03, right? It was 0.75 times 0 is nothing, and then when you subtract the 0, you just get 0.03. And finally, you get 0.0195. Okay? Finally, we'll do the last one. Okay, I'll let you do this on your own. It's pretty simple. You just follow the same procedure, and what you get is minus 0.3871 and 0.0464. Okay, so this is what happens after you do just one example. Okay, so we're going to do it again. For the next example, you do that update and so on and so forth, and then we finish. Okay, so that's the first example. This is the second one. Okay, example number 2, all right? So example number 2, what was that? I don't quite remember. It was minus 1, minus 2, and 0.25. So the example that we have, okay, it was minus 1, minus 2, and the expected output was 0.5. All right? 0.25, sorry. 25. Okay. Just want to double check to be sure. I'm pretty sure it's 0.25. Yep, 0.25. Okay, so here we go again. We're going to do this stuff again. But remember, when you're doing these calculations, you are using the weights that were just recently updated. So your W1, W2, and W3 are all these weights that we just computed previously. So you're using those updates in order to compute the forward and back prop for the next example. Okay, so we do this all over again. So forward prop. Okay, so initialize the input layer to have a bias, and then you have the training examples. Each feature goes into a column vector as so. Okay, and then if you want to compute the inputs that are going into each of the hidden layer neurons individually, you take the first weight matrix, transpose it, and then you multiply it by the outputs that come from the input layer. So now, remember that this W1 has changed. This matrix is equal to this guy over here, this one. So we have to use this one to do our computation. Okay, so I'm just going to copy this. So once I'm finished this, I'll take a break. All right. So x of 0, which is 1, 1, 2. 1 minus 1, minus 2. Okay, so when you compute this, I'll bore you the details, and I'm pretty sure you can do this on your own. When you do this computation, what we get is minus 0.0065, okay, and minus 0.0076. Okay. Calculate the inputs that are going into the outputs that are coming into the out to the first layer, out from the first input layer. So we've already calculated the inputs. Now we're going to calculate the outputs. So append a bias, and then you just apply the activation function to each of these elements individually. Okay. So when you do this, it's by fluke that it's going to equal the same thing because these numbers are so small. So when you do this, this is equal to minus 0.0065. Obviously, I won't do that for the final exam. You will see a change. This is just the numbers that I chose, and they unfortunately didn't work out. But I made the problem set already, and it's released, so I figured just roll with it, I guess. Okay, so calculate the inputs that are going in between the first and second hidden layer. So take your weight matrix, transpose this, and multiply by the outputs that are coming from the previous layer. So W2 now is this updated matrix, which is right over here. So this guy right here. This is the one that we take. So we don't take the ones that were initialized. Come on. Okay, one more time. Okay, I'll just do that, and I'll just erase what I don't need. So here. Okay. So we have this, and then you multiply this by x of 1, which is 1 minus 0. Transpose. So I should probably transpose this. So we have, let me just write this out, and then I'll just delete what I don't want. And there's 0.0195. Okay, so we'll get rid of this. Bless you. Okay, so here, and then 0.65 and minus 0.0076. So when you calculate this, it's only one value, and in this case, it's only minus 0.0072. Okay? So calculate the outputs that are coming out of the second hidden layer. So we have 1, and then apply the activation function to that input. And actually, it's just going to be the same thing because when you actually compute it, it works out that way because the number is so small. Okay? And then finally, calculate the inputs that are coming into the output layer. So we have W3 transpose and then X of 2. And then this weight matrix was right here, this one. We don't use the initial ones anymore because we did an update. Okay? So take this, multiply this by 1. Oops, and I need to transpose this. So 0.0464. Let me just remember that number. Okay, whatever. So we have minus 0.3871, 0.0464. This was W. Okay, just want to remember. Yes, good. So here, and then 1.072. Okay, so when I calculate this number finally, this is equal to minus 0.3871. Okay, so that's good. X of 2, S of 3, and then finally I need to calculate the output. So in this case, you just apply the activation function to minus 0.3871, and in this case, we get something slightly different because the magnitude is slightly higher, which is 9.1. Okay, great, so we're done that now. So that's forward prop, now you're going to do back propagation, okay? So back propagation. Okay, so when you do this, what you need to do is you have to calculate the sensitivity of the output layer. Okay, so you take the predicted output, subtract the expected output, and then you multiply this by the derivatives of the inputs that are coming in to the output layer. Okay, so X of 3 was minus 0.3691. The expected output was positive 0.25, I believe. Yes, it is. Yes, 0.25. Okay, element-wise, multiply this with 1 minus. There's only one output and one input correspondingly, so 3871. Okay, remember, don't do any more work than you need to unnecessarily. So we've already calculated this product right here, which is this here. So all you have to do is just substitute 0.3691 into here. So this gets replaced with minus 0.3691, And when you do this calculation, when you multiply everything out, we get minus 0.5348. Okay, that's good. So now you calculate the backpropagation for the previous layer from the output. So in this case, you do S of 2, multiply this by the weight matrix from the next layer, but then you remove the first row. Okay? Okay, so just a recap, W3 from before was equal to, let's see here, it was minus 0.3871, 0.0464, okay? So if you want to remove the first row, just get rid of the first element here. And in this case, we have 1 minus G. This is all squared. And then you're just multiplying by a single number, which is fine. So we don't need that element thing anymore. It's implied. But you get 0.0464, and then multiply by delta 3, which is minus 0.5348, okay? So G of S of 2, we've already calculated this from the forward prop from before. So let's see here. G of S of 2 is right here, this guy. This right here is G of S of 2. Okay, so in this case, you're just substituting minus 0.0072 into that equation here. Okay, so you get 1 minus 0.0072, I believe it was a minus. And then these numbers right here. Okay, so when you calculate these numbers, we get, let's see here, it was minus 0.0248, or minus minus 0.0248. Okay, finally, you have the last one. Okay, and then take the weight matrix, next layer, remove the first row. So let me just recap and get what that matrix was, because it's been a while since I've used it. So here, and then, so it was here, this guy. So this was, okay? So I need to remove the first row, so get rid of this guy right here. I'm left with, just that one, okay? So S of 1 was equal to what exactly? It was this guy here. So it was actually one, let me see. Was it G of S of 1? Yes. So it was, sorry, here. I'm losing track. So it's this. And then what you need to do is you have to apply the activation function to each of those separately. So 1 minus, and then it was 0.065? Yeah, minus 0.0, okay. So minus 0.0065 squared minus 0.00, can't remember, 65 and 76. Let me just clarify this, sorry. 6576, okay? And then this time you have to put this in because now it's implied. So W1, so we have this matrix, 0.019 minus 0.0207, okay, minus 0.0111, 0.00012, and then you multiply this by the sensitivity of the, let's see here, did I mess up? Yep, no, this is good. So then you multiply this by what this was. This is minus 0.0248, okay? So W1, yeah, hold on a minute. Oh, sorry. Oops, I copied the wrong matrix. My bad. This is W1. I need W2. I'm really blind. So get rid of this. Surprised no one caught that. Hey, I make mistakes too. This one. I need this one. I copied down the wrong matrix. I'm surprised you guys didn't catch that. This one. So, okay, I'm just going to write it down. I can't seem to freaking copy it. Okay, so get rid of this. Sorry. I was wondering, like, yeah, the matrices don't match. That's really, really weird. I'm like, yeah, the dimensions don't really match. So we have minus 0.0069. Sorry, I apologize for that. 0.03 and 0.0195. Apologies. So get rid of this guy. Okay, this makes more sense. So you have 0.03, 0.0195. Multiply this by minus 0.0248. Okay, okay, this makes sense. So now you have a 2 by 1 column vector, this is now a 2 by 1 column vector. So when you multiply, and you put everything in here, the final matrix we get is equal to, it's again very small, and then minus 0.0005. Okay, so we need to calculate the area gradients now. Okay, I'm just going to speed up the computation here. I'll let you guys, verify this yourself. So when you do this, we get minus 0.0007, minus 0.0005, and we get 0.0007, 0.0005, and minus 0.0014, and minus 0.001. Okay, I'm just going to write down the final answers for you, and then we'll take a break. Because I'm pretty sure you're probably sick to death of these calculations by now. Let's get on to something a little different. Okay, so when you calculate this one, this is equal to minus 0.0248, and this is 0.0002, 0.0002 again. Okay, and finally you're going to do it for the last one, okay, which is 0.5348 and 0.0038. Okay. All right, so those are the gradients, and then I'm just going to give you what the final updates would be. So you're going to take these ones and you're going to, apply a learning rate to each of these matrices. So finally what you get is minus 0.0099, 0.01, 0.0184. I'll just write down the equation just to be sure that you know what you're doing, and then we can go from there. Okay, so minus 0.0126, 0.0183. Okay, remember, if you want to compute this, you just take the old one, and then you apply a learning rate, and then you take the corresponding error gradient matrix for that. So, let's just doing that. Just doing that computation. Okay, so you get 0.0118, 0.0299, and 0.0194. Okay, again, just going to take this guy and just do it for the second matrix. I'm just going to write that down for you, so you know what you're doing. Come on. Okay. And this is 2. And finally, we'll do the last one, and we're finished. Okay? So, this one is equal to 0.014, 0.0435. Okay? And you just do this. I'm not going to do that for you. You can figure that out on your own. Okay, that's it. That's it for the neural networks review, all right? Okay, so we'll take a break. We'll come back, and I should be able to finish off the view in the second half. So let's take a break, and we'll come back in about 10 minutes.